Hello everyone. Today a customer sent me a server UPS that was damaged by a lightning strike and asked me to repair it. However, after taking measurements, I found that the main control board was completely destroyed. The only reusable part is the transformer, which I will repurpose to build a completely new pure sine wave inverter. The customer agreed with this solution, and that's exactly what today's video is about. This video is sponsored by JLCPCB, one of the leading PCB manufacturers. Their PCB quality is excellent and the production time is extremely fast. If you've never used their service before, you can check out my quick guide below. I'll show you the simplest way to order PCBs from JLCPCB. First, you need to create an account. You can sign up quickly using the link I've placed below this video. Then, upload the Gerber file that I provide. Once the Gerber file is successfully uploaded, you can do a final check of your PCB using the built-in 3D viewer. This tool is very useful. You can easily spot design errors and preview how your PCB will look after fabrication. Next, you can choose the PCB color, material, and many other parameters. After completing all the settings, you can add it to your cart and proceed to checkout. Don't forget to apply discount codes to optimize your PCB cost. JLCPCB is currently offering great deals on 6-layer PCBs. If you have any 6-layer PCB projects, don't miss the chance. Sign up now and take advantage of these excellent offers. This circuit board is very simple. I removed many peripheral components and replaced their functions with a small microcontroller, so the design is straightforward and easy to assemble. In this video, I'll focus on the main question. Can we reuse the UPS transformer and turn it into a standard inverter suitable for normal household use? This is the main board of the UPS. There are quite a few components that can be reused, such as relays, heatsinks, and capacitors. However, we'll deal with those later. For now, we'll focus on these two very heavy transformers. They can deliver up to 3,000 volt-amperes of power. Each transformer has a primary winding made from copper foil, while the secondary is split into 4 terminals with 3 different voltage levels. For our purpose, we only need the 2 outer terminals, which provide the highest voltage. The interesting part is that with these 2 transformers, we can easily use them for either a 24-volt or a 48-volt system. For a 24-volt system, both the primary and secondary windings are connected in parallel. For a 48-volt system, the primary windings are connected in series, while the 2 secondary outputs are connected in parallel. First, I'll test with just one transformer. You'll need an additional toroidal core like this. It is wound with 1 or 2 turns and connected in series with the primary winding. As you know, one leg of the H-bridge is driven by a high-frequency SPWM signal. If we feed this directly into an iron core transformer, it will run hotter and the conversion efficiency will drop. Filtering out the high-frequency components before they enter the transformer helps improve efficiency and reduces the no-load current. At this point, I've connected the transformer's secondary winding to the circuit, and the output is also connected to a wattmeter to measure voltage and power. The input voltage for this single transformer setup is 26 volts, which corresponds to a typical 24-volt lithium battery system. As you can see, the no-load power consumption is around 17 watts, which is acceptable for an iron core transformer. With a 300-watt light bulb as the load, the DC input power is 330 watts, which corresponds to an efficiency of about 91%, quite decent. The transformer produces a slight hum, and the MOSFETs are operating well without overheating. This is the output waveform, a near-perfect sine wave. Of course, that's with a linear load. With other types of loads, the waveform may degrade slightly. Next is the setup using two transformers. In this configuration, the primary windings are connected in series and the secondary windings are connected in parallel. The most critical part is correctly identifying the start and end of each winding. If you get the connections wrong, the MOSFETs could fail instantly. When operating at 48 volts, the no-load power consumption has doubled to over 30 watts, which can be a burden for smaller energy storage systems. Efficiency at light loads also drops significantly compared to the 24-volt setup. However, the output waveform remains very clean. I tested it with a hairdryer and a light bulb as the load. The total power consumption reached 1.5 kilowatts with a DC input of about 1,650 watts. The efficiency is over 90%, which is not bad for a UPS transformer. However, with around 150 watts of losses in the MOSFETs and the transformer core, we will definitely need a cooling fan running continuously. At this point, my testing is complete. The conclusion is that we can absolutely reuse a UPS transformer to build a pure sine wave inverter. The downside is that the overall efficiency would be about 1 to 2% lower compared to a toroidal transformer. I'll inform my customer so they can choose between a 24-volt or 48-volt system, and then I'll assemble everything into a new enclosure. In the end, the profit from this job is around $50. Thanks for watching my video. Thank you very much.